Hello, everyone. Thanks for being here and letting me share our story of how we up-leveled our data infrastructure using Iceberg at Airbnb. My name, Edgar Rodriguez, and over the last few years, I've worked on bringing Iceberg into the data warehouse at Airbnb. And so today, I'll share some of our journey, some challenges we faced also, and I will briefly talk about our future plans with Iceberg. Um, This talk mainly focuses on what we call Icehouse, which is the internal name we coined early on for our data lakehouse when we started to collaborate with the Apache project. This was around 2019. And so this evolution spans over several years, including open source collaborations, data stack upgrades, large migrations, and a whole set of challenges with aim to simplify and improve our data community's experience when working with data. Uh, this is a little bit of a journey and evolution, simplified, of course, but Airbnb's journey to Iceberg is very similar to most other data infrastructure in the industry. We originally had Hive as our compute and table formats, of course, and some workloads in Presto, Trino, Spark 2. So we had a multitude of compute engines accessing all this data in HDFS. As the total number of data sets and tables increased, so did the load on our HDMS, our Hive Metastore, and so we ran onto multiple stability issues. Given that the Hive Metastore rely on a single MySQL database, it wasn't really possible to scale it horizontally. In addition, instead of S3, like I said, everything was on HDFS, which resulted on on-call alarms and name node scaling issues, all that set of challenges that were there. We decided to move our storage from HDFS to S3 in 2019 to address some of these challenges. This, of course, reduced our operation burden, and to some extent, we no longer had to scale an internal storage cluster, which is the HDFS that we had. But the Hive Metastore was still a scaling problem. In addition to this, we discovered new challenges like instead of faster listing operations like in HDFS, which everything's in the name node, S3 now was slow doing listing of prefixes whenever queries came in and span multiple partitions, so causing performance latency and other issues in our jobs. We worked around this also by implementing a prefix caching layer, which was on top of AWS S3, and so we were able to tune that better for our partitioning and our prefixes, and so also avoid some throttling errors that overall it was a net improvement for our user base. And so, but at the same time, we started to evaluate other options. So this was 2021 when we kind of like set the path towards adopting Iceberg and unlock some of the new data development patterns. This also pushed us into a strategy where not only our storage needed to evolve, but also a lot of our data stack infrastructure. And this is just because of how Iceberg was shaping in some way the way compute engines, mainly Spark, was going to adopt some of these features. So some of the features that we really liked were Iceberg native partitioning and schema evolution. It helped provide reliable statistics for data pruning. And so transactional guarantees were also very, very important for our ecosystem and supporting updates and deletes. What's going to open a set of new use cases in the infrastructure. And so we started collaborating with open source. We contributed to the Hive read path, which was kind of like the strategy that we said. We were only going to support Hive reads, and everything else was going to migrate to Spark. And so this also opened up a new set of challenges, which is how do you adapt the whole ecosystem to work with Iceberg. And so this is how it looks now. It's a much more simplified architecture in our data lakehouse. We still use Spark and Trino for offline compute engines, and Flink is starting to take a major role for real-time use cases. And so we also added an internal API that you see there as Icehouse API. And this acts as a wrapper on top of Iceberg and abstracts or extends some of the native Iceberg library capabilities. This was required in order to make the whole ecosystem work with previous tooling that was heavily Hive-based. For example, systems that used sensing of partition data, which partitions don't really exist in the Hive metastore, right? Well, for Iceberg tables, as they are only pointers to the Iceberg metadata. And so how do you make all this work in this new ecosystem? So behind the scene, we rely on Iceberg as table format and S3 our actual data storage. So like I said, compared to our previous architecture, the system is much less complex, better abstracted, and with more interoperability thanks to the adoption of Iceberg as a common middleware layer, thanks to fast adoption on the open source community. Airbnb's data lakehouse stores hundreds of petabytes, and most of the current processing is in batch. In batch means that every day we have batch jobs that process all the data in different cadence. Not all happens at the same time, which is 0 UTC, but depending on the job, they can change that scheduling. But at the center of it, the smallest unit of work is the partition. So therefore, we needed a way to detect when partitions landed in certain data sets. Also, given the introduction of Iceberg, we needed a table maintenance system that is able to maintain tables at scale. And so our current maintenance system processes around 26 billion objects every month. And so this is required in order just to keep a healthy ecosystem for Iceberg tables. Some of the efficiency improvements with Iceberg, well, our first use cases that we onboarded into Iceberg were all infrastructure-owned data source events. So basically, we handpicked a set of pilot use cases that we could see what is the effect of bringing Iceberg into the data warehouse. And so we selected our login events, which accounts for a large portion of our data warehouse. And this is one of our raw data sets. With Iceberg, we were finally able to move to a newer ingestion paradigm where a single table had both a day and a day-hour partitioning spec. Instead of needing 2 duplicate tables per partitioning spec in Hive, we will see a slide later about this setup. In addition, we were able to migrate to C standard as Iceberg has its own read-write path, allowing us to leverage what was not possible before because our Hadoop and Hive libraries were too old. And so therefore, with Iceberg, we were able to centralize our compression story around C standard. And so we gained 7% on average. This is consistent with other findings from other companies, but we saw on certain data sets that we were able to achieve a higher rate of compression, between around 20 or 40%. Overall, the results were outstanding. 70% reduction in compute savings and 95% reduction in wall time for read queries for these tables. So we had a lot of use cases that were really successful in this. But of course, it all depends on the selectivity of the queries and the layout of the data. But not only that, we were able to open up new use cases. Some of the new use cases that Iceberg has enabled at Airbnb are, first, it allows us to decouple the cadence of data production and consumption. Because Airbnb's data is processed in batch and is still partition-based, using different partition specs, users can produce data hourly, and consumers can choose either to consume it daily or hourly as well. And so behind the scenes, the platform compacts the hourly data into a daily partition, and we provide the same guarantees and semantics that we had in the Hive world. Our streaming ingestion using Flink has also been simplified. with the Iceberg's native Flink support. This is a major feature that we're now pushing forward, and we see this in the industry as well as more processing is moving to near real-time ingestion. And there are a lot of use cases there where Iceberg is really, really important. And lastly, our schema evolution and partitioning evolution, as well as time travel and rollbacks, have allowed users to have other different types of workflows. And mostly, they all geared towards having a more dynamic workflow where they don't have to run backfills because they changed column or they changed partition spec because they wanted better data layout. And so now I'm going to talk about Jitney, which is kind of like the first use case that we onboarded into Iceberg. And we saw a lot of benefits here. This is one of the major successes at Airbnb with Iceberg. And so Jitney is our event ingestion framework, storing certain events in the data lakehouse coming from Kafka. Jitney provides data on an hourly and daily basis. As seen on the left side of this slide, we used to have 2 copies of the same table in Hive for our raw logging events. The hourly tables were necessary to be able to keep our ingestion latencies low, and some use cases required hourly data. Most of our warehouse operates on daily granularity and assumes a day-based partitioning. So for everyone else that consuming this data on a daily basis, we also needed a solution. Once a day has passed, all the hourly data isn't really valuable. Squaring it is also most done at the granularity level of the day, right? So once jobs that are processing data hourly, after one day, the value of that hourly data cadence goes away, and so everyone consumes it daily. To leverage better compaction and compression, we also created a daily table copy that all downstream jobs relied on. The hourly table had a low retention to save cost, and so therefore it was only temporarily spaced for downstreams to access that lower ingestion latencies and rely on hourly data. So with Iceberg, what we did was to set up a table which would get rid of the 2-table setup, and we were able to have in this Iceberg table 2 partition specs. One with just DS, which is daily, and the DS hourly, day-hour partition spec. The data is written with the hourly partition spec, and on day boundaries, we created a compaction job that would basically take all the data files that cover the whole day and rearrange the metadata so that they are now written into the day partition spec. Now, we had some optimizations in this compaction job because sometimes we do want to rewrite the data if the data files are really small for like low volume events. But for large volume events, we didn't really need to rewrite the data files because they were already on a really good size. And so the only thing we did was to manipulate the Iceberg metadata so that it fit into the new day partition spec. And so this saved a lot of compute resources because we don't have to rewrite data. And so this showcases one of our use cases that had a lot of impact at Airbnb with Iceberg, but how do we get there? And so the journey that we took first was to realize that the problem were a lot of assumptions with how to manage data with Hive. And so we decided to make Iceberg our default storage core in the Airbnb's data lakehouse. In order to ensure that we have a complete data infrastructure product for our data engineers and data practitioners at Airbnb, we wanted to offer a self-managed, self-optimized, and fluid storage layer. To achieve this, we proposed to our leadership that we invest in Iceberg as a core storage format for all the use cases and build infra-level systems that will take care not only of housekeeping operations like retention and compliance, but also optimization and self-tuning. And we can see this in this slide, which showcases essentially the structure of how we wanted to work with the new storage layer. What Iceberg brings to the table is essentially a middle layer that abstracts all the storage optimizations that we can do on the background for the user, while at the same time providing new use cases. Migrating to this Icehouse abstraction-based storage layer allows us to unblock multiple new use cases. For example, we dump our online database mutations on a daily basis to a data lake, and giving Hive's inability to support row-level updates or deletes, the current solution created a full snapshot of the database every day. So you can see that this pattern is very wasteful in terms of storage. And so with Iceberg row-level delete support, we were able to redesign this architecture to have a true CDC pattern and only store mutations that happen day over day, but still giving users the view that they need to do and validate their analysis. This has potential to reduce our storage footprint by an order of magnitude for online databases, replicas stored in the data warehouse. Similarly, with Iceberg, we can now support low latency real-time ingestion through Flink using the Iceberg connector with a commit frequency that is about 15 minutes or lower, up to 5 minutes. This unlocks a lot of near real-time use cases that generally we were not able to support in the past. In addition to the new cases, we can also now do automatic storage level optimizations without ever affecting users' jobs or queries due to Iceberg isolations guarantees. Based on our added of read queries and patterns, on individual tables, we can build systems that recommend new partition schemes and sort orders, and then apply them to these tables to better optimize the data layout. Partition and scheme evolution were also very important. They enable our users to evolve their workflows in a way that it wouldn't be costly for them. So there were a lot of challenges along the way. And so through this vision is very grand. Migrating a whole data warehouse with lots of data into a new table format is not an easy task. But not only that, there's a lot of built-in Hive assumptions along the way. And what I mean by this is when you work in a data system that has been there for many years, there's a lot that has been built around the ecosystem, right? So if you have all data engineers that they're very, very knowledgeable about Hive, lots of tools have been built around it. And so how do you go about changing those set of tools and patterns and ways of working without disrupting them and bring a new table format that it will add new features, but most importantly, you don't want to disrupt how people use their day-to-day features, right? Even though the new features bring more added value. And so that's one side of the equation, and probably one of the ones that are largely overlooked by, migration processes. But at the same time, we had other challenges like providing a performant and secure S3 access, standardizing our compute engines at Airbnb because we had many and with different versions. So we had Spark 2, 3, Hive, Trino, Flink, and also Starbucks. So we had tons of compute engines, so we needed to ensure that the Iceberg experience was the same across all compute engines. So this triggered a set of migrations just to standardize the compute engines that we were using. Not only that, Spark 2, when Iceberg started, it supported Spark 2, but was quickly removed from the support. And so we needed a way to go to Spark 3, where the data frame API has full support for V2 tables, and therefore be able to support everything natively. Airbnb's workflow, infra, and data engineering communities has years of tooling built around any of this. Airflow, common workflow orchestrator system, heavily relies on sensing Hive partitions, and therefore we needed a similar solution for Iceberg. Our long-term goal is to move away from these legacy patterns and move to a new efficient data processing paradigm, but some of this tooling was necessary to build along the way. And the new paradigm for building data is not necessarily depending on partitions, because as we know in Iceberg, partition can change, and therefore everything breaks, right? So you cannot sense on partition. You need to sense, has this data changed? And therefore, from there, users are able to ask what data has changed and then process that amount of data. Lastly, we had built a smooth, automated, and safe way for users to migrate. Everyone needs some migration framework. And so we built our internal tooling, which was a UI that had a one-click button where people could go, click it, and migrate their tables. That was the first phase of the migration. And so just taking a little bit deeper about these challenges, in the area of S3 and access control, we needed to implement our own access control, which was already supported in Hive. We needed to backport, or well, forward implement into Iceberg. And so, of course, we have our own Icehouse catalog. And then we have our FileIO implementation, which provides all the FileIO secure implementation details, which we use a token vending system in order to provide access to the data files and metadata files. We also have a lock-in mechanism that is based on DynamoDB. And so we don't use the Hive transactional system for locking tables. Instead, we use DynamoDB, which we already had experience with, and we were able to implement in our own custom catalog. Like I mentioned, we had to update the whole data stack, compute engines, deprecate Hive. Initially, we just made Hive read-only, and we standardized to Trino for analytic use cases and Flink for streaming. So the whole strategy was a forcing function to update our data stack. We consolidated on these compute engines, which had a very well supported core in Iceberg. And so along the way, we also worked around issues like Hive reads were not as performant as Spark, and that's an understatement. And so we had to work around a lot of filter predicate translation. A lot of the filter predicates in Hive, in the Hive implementation, were not even translatable to the Iceberg filter predicate that could be pushed down to the scan planning. And so you would end up sometimes scanning more data that you needed. The Trino needed also a metadata caching in order to be able to handle Iceberg tables with large number of data files. And so as the metadata grows, you end up running scan planning that takes longer. And so for analytic use cases, we needed a caching that was there. And this is also because Trino does not implement distributed planning yet. Now in Spark, you can enable distributed planning for Iceberg, and that problem is largely solved. Flink ingestion also is another set of challenges because it uses equality deletes, which requires aggressive compaction in order to maintain read performance. And so for writes, it's really good, but the reading performance needs to be heavily maintained. So we work around some solutions for that. One of the solutions we have is to convert equality deletes into positional deletes in a post-processing table maintenance system. And so we're also looking into ways to optimize equality deletes in order to provide better performance for reads. So in terms of the workflow orchestration tooling, Airflow's Airbnb de facto workflow scheduler is Airflow. We created Airflow, and so we've been using it since then. So we needed to create a system that was able to answer the question, has this partition landed in the table? And so for that, we have our own service, which is based on the Icehouse API. And what it does is it basically goes and checks on the metastore for this table, has this set of data files arrived, right? And so the data files match a partition, and so we return, yes, there's a partition. Now, because everything is batched right at Airbnb, we have guaranteed that there's no incomplete data. So we know that when a commit happens for that set of data files, the partition has landed. This is not ideal if you want to support um, um, alter or insert statements just to add data, but that's why we want to move to a different paradigm. So the migration framework, we built a migration framework that runs a finite state machine to automate the migration tables at scale. This tool handles all the migration failures, rollbacks, and other conditions without user intervention. At scale, with hundreds of thousands of tables to migrate in our data lakehouse, a tool like this is key to fully deprecate Hive tables. After onboarding a few pilot use cases to Iceberg, our migration strategy had two phases. First, there was a user-led migration effort where we made available a one-click tool that migrated user tables to Iceberg. The whole idea was to eventually this to be fully automated, and that's what we're doing. We're just batch migrating the whole data warehouse with this automated tool that now is fully automated. And now, the problem of the Hive assumptions and the patterns on how we work. I put this quote here that we cannot solve a problem by using the same kind of thinking we used when we created them. This quote made me think about the challenges that we as data people that works with data are used to do, right? We have a set of toolings that we are used to work with, but at some point, if we have a set of challenges that we've worked around, we need to think about a better way to upgrade our data stack and provide a simplified way to work. And now I want to exemplify that with the user experience that works with data. In the Hive data world, when we had, there was a high knowledge burden on the user. So the user needs to create a table, needs to know the schema, partition inspect, table format, file format, in our case, airflow dependencies. This pattern is great if nothing changes, if everything's static. You don't need to change the schema. You don't need to change the partitioning. Otherwise, you would need a backfill. And so there's a higher maintenance cost also on the user side because you have to think about what are the layout and what is the layout of this table on the data side, and so how can I optimize it? In the Iceberg world, what we want to enable is a simplified knowledge burden for the user, meaning that users only need to know the schema and the partitioning, kind of like in transactional databases, right? You just need your schema and your indexing strategy. And so with that, you can create a table. And if you want to read a table, then you only need to know an interface with the schema. Then under the hood, the platform and table owner are the ones in charge of optimizing access to this table. So therefore, evolution is back in the design. If you want to make schema changes, they're transparent, there's no need of backfills. And so with this, the platform can take optimizations automatically, compacting or repartitioning based on other information like filter predicates that are being used on that table, etc. And so therefore, there's a declarative config-driven optimizations that can be set. So what's next? With Iceberg, we can now analyze the storage layout independently from how the user consumes the data. This allowed us to think about possible optimizations that were not possible in the past, such as evolving partition specs, improve the performance, and yield better cost savings. Additionally, now we're able to track filter predicates across the tables and allow the platform to determine when is the right time to repartition or sort the data. We're also working on optimized CDC reads based on branches in Iceberg. And so every time we ingest mutations, we want to provide a read-optimized branch to the user, while at the same time reducing the cost that it takes to store that data. And lastly, our declarative data movement. It's a project that we are starting at Airbnb that with the Iceberg adoption, we can now finally leverage some of the new features and move to the has data changed model versus has partition landed. As mentioned before, Iceberg will allow us to unblock near real-time near real-time use cases that were previously not possible or need a different compute engine. And so therefore, our declarative data movement initiative aims at enabling semantically aligned data movements across data sets in near real time. So Iceberg is at the core of this new technology at Airbnb. And with that, I want to thank you for your attention. It was a pleasure sharing our story at Airbnb and how we up-level our data infrastructure with Iceberg. By the way, we are hiring. If you're interested in working in any of these that you've seen, please apply, join, reach out to me. I'll be happy to point you in the right way.
Right, thank you very much. Okay, I can yell. No, okay. It was just slow. It's all right. We have some time for questions. Are you ready? So, okay, we have plenty of time for questions. So yes, go ahead.
My name is Krish. I'm from Roku. So we are on the process of migrating from Hive to Iceberg, maybe late in the game. So in terms of your experience, like with the Iceberg version V1 to V2 or V3, so how hard is to migrate from one version to another version?
In our case, it wasn't hard at all. Just because, like I said, we mostly use the core features in V1. So V2 was sort of like transparent. Mutations, of course, that's a new use case that we started to onboard. But for everyone migrating, like I said, there's a lot on the environment that doesn't even use the new features, right? So our first goal is let's get you into Iceberg and migrate our tooling, make it work with Iceberg. And then from then, we start also influencing the tooling around to adopt the new features like branches, mutations, right? And so to us, it was a moment where we need to migrate you to a version that is compatible with Hive as you use it. And then from there on, evolve our tools.
Yeah, one more question. In your slide, you said about 70% resource savings while migrating from Hive to Iceberg. Is it only a table format, or like were you using like Hive for a ETL as well in your in Airbnb?
Yeah, so it included several things. Included, of course, migrating all our stack, like Spark, using better, I guess, data layout, statistics, but also, like I said, Iceberg was kind of like the forcing function to improve our data stack. And so therefore, we can now leverage AQE from Spark. We can leverage other features that work much better. And so I think the point of this talk was like, Iceberg was the forcing function to get you into what is the industry moving to, right, in terms of data stack and features and optimizations.
One last question. As part of this, why you guys stuck with HMS? You could have gone to like Iceberg REST catalog or maybe Gravity now, Polaris, whatever.
Yeah. REST catalog is definitely our choice. That's where we're going. We're still evaluating whether we have to implement our own REST catalog or go with some other one of the open source catalogs out there. But yeah, definitely, like I said, kind of like incremental. When there's a large community of data practitioners in a company, it's very hard to just jank something and replace it. So we have to be very careful on how we move forward. But yeah, that's the path.
Hello, I have a question. One for the sorted column. Yeah, you said you have some tools to help you to select some sorted column. Definitely, we see the benefits of sorted some columns with a much better compression. But you don't want to sort all columns. Yeah. So what's the metrics or trade-off? How do you select which column you want to sort it?
Right. No, that's a great question. So one of the things that we're experimenting with, and this is work that is happening, it's a table analyzer. So basically, a table analyzer is going to go and sample the table and run a series of combinations of that sorting and evaluate what's the size of us writing that data, and basically pick one of the compression configurations that are better or are the best in that sort of I guess, combinations of configurations, right? So we are looking into the data set, of course, is standard, but also compression level, right?
Okay.
And so we kind of like work around those variables.
Okay. So another question about the partition sensing. You have some tools to help you to look at the. I mean,
Yep.
how do you? I mean, do you look at the S3 folder? How do you prevent the early materialize? Because I have a bunch of data to accumulate. You see the folder immediately at the beginning of the write. A lot actually all the data is I mean materialized, but your sensor could be give you a signal. Oh, we are ready to for you consume.
Right.
How do you prevent these events here? We face the same issue.
Yeah.
Yeah.
So I think one of the things that helped us on that front is that we standardize to, or well, we cannot enforce because we didn't support inserts, right? We didn't support adding data. So we have this requirement that data needs to arrive in batch. So therefore, once a query comes in, has this partition landed, we check that there in the metadata, the partition is there, right? So if the partition is there, we have a guarantee that the partition is complete because that's the contract on our on all the systems, right? Workflow orchestration, pretty much everything else that works like that in batch. Streaming is a different story, but yeah.
Okay, last question is like you have like hourly table, daily table, you merge into one
Right.
Iceberg table. I believe this is because I mean hourly table generate too many partitions,
Mhm.
causing and planning over time. Yeah.
Right.
Well, after you migrate to one partition, did you do some I mean data trimming did you still see some like too many partition planning, timeout these things? Because I don't know whether Airflow do pure time purging data or logs. Whether or not I mean we have same issue. We have two set of table. All the right now we move to Iceberg with same table, but we are just like 1 month, 6 months.
Mhm.
We didn't see like 2 years. Whether or not I mean with 2 year data planning of
I see.
overhead become worse. Yeah.
Right.
I just curious. Yeah.
Yeah, so this, what we did with Jitney was to compress daily. So we compress every day. And so the way we onboarded to this is because they had two tables. We migrated technically the daily one. So we didn't have to do any compression like on a historical time frame. And we just, now the ingestion happened hourly. And so basically in that same DAG, we just added a compression step after data lands on the daily basis, right? And so we compress every day so that we don't have to go and compress on a historical data set.
We have time for 2 more questions. 1, 2, 3.
Hi Edgar, this is Abhijit and
Hi.
I'm from AWS.
Yes, hi.
I remember I worked with you before to implement the S3 cross-region replication for
Yeah.
your DR strategy for the Hive tables.
Right,
But with Iceberg, with the complexity of metadata replication,
right.
how you're tackling that?
Yeah, so yes, disaster recovery on Iceberg tables is complex. We have a very good tracking of all data files that we need to recover, but we need to recover also the metadata. And so what we chose to do in this case is, because generally metadata is going to be much smaller than the data, we just recover all the metadata that we know about of this table. And then we select, based on the metastore, we know what was the last pointer that that table had. And so basically we just rebuild that in the metastore and point to the latest JSON file that we have as entry point into the Iceberg metadata. And so that way we can recover metadata and all the data that was used. And then we have kind of like a validation process that checks, is this fully recovered, is it okay, and register into the Hive metastore just to basically make it available.
Hey Edgar, this is Prasad from Data Palago.
Hi.
It's a 2-part question.
Mm-hmm.
You mentioned like 95% latency improvement,
Yeah.
right? So what are the top 2-3 things that really contributed to that, right? Are you like processing less data or whatever, right?
Yep.
And second thing is you seem to be on AWS, right? You're
Yes.
using S3. So is it a EMR version of Spark or is it a open source version of Spark or any other optimizations there?
Yeah, great
Yes.
questions. So, the first question, we saw a couple of use cases where just the statistics, just as the statistics with sorting, like help tremendously, 80, 90%. And these were really, really important use cases that had, several hour processing that was down to, I don't know, like 10 minutes or 3 minutes, right? So basically just if you have a really important use case where you need to lower that read time latency, sort the data if you know the read pattern, and leverage the statistics. I think that's a huge tool that, it's been in Iceberg since the beginning, but, there's a way to leverage it. And so that was one. For Glide, I think we mostly leverage all the data stack, right? And which is AQE, everything that we can use with Iceberg. But yeah, that would be some of the things we did. And your second question, we were using EMR, the Spark flavor, but we had challenges because our Hadoop ecosystem is kind of old, so we had to build our own Spark 3 flavor. And so that supports all Iceberg features.
Hi, I'm Fennel from Slack. Great talk, by the way. Wanted to ask, so at the end you mentioned that you want to move your workloads to declarative data movement where people, downstream users, they see whether the data has changed instead of like reading partitions. But now when your orchestration framework is tied to Airflow, where you have some jobs that read daily or hourly, and initially you mentioned that many of your tables are also structured in date partitions and hour partitions. So how do you foresee, like maybe looking at Iceberg snapshots, using that with Airflow and the downstream jobs?
Yeah, definitely. I think that's some of the work that's happening right now. So there are a couple of things that are changing in the ecosystem to support the new pattern. One is we're implementing a signal service instead of the pull mechanism of Airflow that senses, is this partition here, right? So every so often, Airflow is asking that to the metadata, and so we're going to change it into a push model, right? So someone subscribes to a certain event, has this data change, they're going to receive an event and kick off their workflows. And then to your point, yes, we're looking into basically snapshot changes or any other changes that we can emit from Iceberg. We already have some events in our custom catalog that basically sends an event if data has changed, right? In our case, because we're still partition based, when a partition lands, it sends us an event. So we can technically flip that pattern, but we're looking at the granularity of those changes that we want to, announce, and so that we can trigger this workflow. But like I said, it's incremental. So first we started with events on partitions, and then we're gonna go down the granularity.
Hi, this is Pandana from CrowdStrike. So my question, given the volume of data you're handling, I was curious if you have explored medallion architecture, or like how do you, handle the volume, especially if you have sub-second response time requirements for some use cases, how do you get to the subset, a smaller, narrower subset, so you can get faster query runtimes?
Yeah, so I think one of the things that we are seeing in our warehouse is that the streaming use cases is kind of like getting more people is trying to embrace streaming, right? And so we're still in a transitioning phase where most data consumers use batch processing, but we're also seeing it in compute engines. Like a lot of people is using Trino more, right? Just because it is compatible with Iceberg and supports lots of the features and like bucketing and everything, right? And so people is really interested now, not just on the ETL and the data layout, but also on like all the other compute engines that they can use once you give them the better features and support, right? And so it is evolving. Yeah, I think we're looking into many options, but like I said, mainly streaming and supporting compute engines that people are really interested in using now.
Thank you. This is all the time we got for now. There's a 15-minute break, then come back for the next talk. If you want to keep the conversation going and ask more questions to Edgar, I assume you're going to be available.
Of course. I'm around, so feel free.
Yes.
Thank
you very much.
Thank you, everyone.